include commercially bought parts, which are going to include the sensor that we use. In this case, we use the piezo sensors. And also it's going to include the mastic rod tapes that we use for attaching the sensors to the pavement. And also it's going to include the silicone adhesives that are also used for attaching the sensors to the pavement. The system also comprises of in-house custom-made components. These include metal plates, which are used for providing a flat and stable platform on the pavement surface. And also we have what are known as end cap crowns, which are there to protect the cable joints. And also another custom-made component is the weatherproof metal cabinet that is used for housing and protecting all the system components. Then as for any system item, the other required component is a laptop computer that will be used for storing your data, performing analysis, and so forth. Then also it comprises of static weigh scales like the ones which are shown here, and these are required for your on-site calibration of your portable WIM system. Then the other optional components that are needed will be a modem communication system. In this regard, your modem, you need it for remote monitoring, viewing, downloading, or performing diagnostic of the system right from your office. However, even if you do not have the modem communication system, you can always go to the site to download your data, do the calibration once you are there. But the benefit of the modem is that it allows you to do all your monitoring, traffic data download, etc., right from your office. Then the other optional component that you might need are what are termed as inductive loops. These are required for the most part in highly congested zones where you have got cars following one another. The reason is that if the cars are very close to each other, at times it might be a challenge for them to be classified separately, and therefore you need the inductive loops. Also, in situations where you have vehicles changing lanes very fast, so you also need the inductive loops to help in classifying the vehicles. But for the purpose of pavement design, for the most part, we focus on the trucks, which have high loading, and therefore you rarely get an issue where you have congested zones or lane changing vehicles, which is mostly occurs for small vehicles. Thereafter, we also have the programs that we use for analyzing our data. These were custom developed programs that are used for data processing, analysis, and quality checks. So everything, the program that we use for our portable WIM system, they were all in-house and custom developed to tailor to the traffic needs for pavement design, maintenance, and rehabilitation. Now, in terms of site selection and the installation process of the portable WIM, what is required is you need a flat surface where your sensors can be stable with no major surface distresses. And also, when you are doing your installation, it's preferable that your pavement surface is warm. This is critical to allow your mastic tape to be able to hold onto your pavement surface. In that regard, we always try as much as we can here in the US to avoid doing installations during winter because you have trouble with the mastic tapes holding onto your pavement surface. The other considerations are that we try to avoid bridges, intersection, and caves. The reasons in particular of avoiding bridges is that whenever vehicles pass over the bridges, you have vibrations, and those vibrations have a tendency of negatively affecting the results. So you want to avoid that. Close to intersection and caves, vehicles will generally be braking, and as they brake, they may end up damaging your sensors. So you want to avoid those areas. And in general, what's recommended is stay about 200 feet away from bridge, intersection, or caves. Also, what is preferred is if you can have a pole on the roadside to allow for the installation of a solar panel, that would be great. Then also you need preferably a well-drained pavement surface so that you don't have water ponding on your pavement surface that can negatively impact the readings and in some cases contribute to damaging the sensors. Now, every time you go for installation in the field, it's critical that you do a system check to avoid a scenario whereby you reach the site only to find that your system is not working or your sensors are not working properly. So it's always recommended to do a pre-check before heading out in the field. The installation time per lane is 1 hour, 15 minutes. Therefore, as you can see, that is minimum disruption. And also you can install on a seal coat surface, asphalt surface, or a concrete surface with no trouble at all. The installation process itself, there is no cutting, trenching, digging, or coring the pavement. Therefore, no damage is impacted onto your pavement. For the most part here in Texas, pavement engineers are generally not so welcoming when it comes to trying to want to damage, cut, or core the pavement. And as such, our system was designed to make sure that no damage is impacted onto the pavement. These pictures here shows 3 examples of installation on a seal coat, which you can see there. That's a seal coat pavement surface. And that is where we have got our portable WIM sensor there. And those are the mask tape that we use for attaching the sensors onto your pavement surface. This is an asphalt surface. As you can see, we have our sensor there. This is a 1-lane road in one direction. This one we have 2-lane in one direction, and as you can see, both lanes were installed. Here it's a concrete road, 2 lanes in each direction, and all of them, as you can see, they are all have installation there. So this just shows an example of that. We can install our portable WIM on seal coat surface, asphalt surface, and concrete surface without causing any damage to the pavement. Now, in this slide, it shows an example of the system check and calibration. In traffic measurements, I must emphasize that calibration of the unit is one of the key elements for obtaining quality results. So for our system, we have a robust calibration check, which comprises of up to 6 stages. The first stage is before heading out into the field, we do a pre-check and pre-calibration of the system at our portable WIM test site, where we do all the testing and so forth. And thereafter, in the field, once you have done the installation, we also do an installation check to ensure that all the systems are working perfectly. And thereafter, we perform now the on-site calibration. In this process, what we do is we weigh a vehicle using static scales, and then we let that vehicle run over the sensors and we compare those weights. And then we can keep on adjusting our calibration factor until the match between the static scale and the portable WIM readings. And thereafter, now we open to traffic. Also, our unit has an inbuilt mechanism for auto self-calibration, which is going to be done continuously in real time as the system keeps on measuring traffic. What this means is we preset a weight, and for the most part, we use a class 9 truck and the steering front axle load. The reason for using a class 9 truck, which I'll show later, is that in the US, 75% of trucks comprise of class 9. Also, the reason for using the front steering axle is that the front steering axle of a truck is fairly constant. It does not change as compared to the rear axles, where the weight is going to vary depending on the load the truck is carrying. So in this case, the average steering axle weight is ranges from 9 to 12 kips. And so we use an average of 10.5, and that we are going to enter into the unit as a reference. And then we set it that when a certain number of vehicle passes over the unit is going to average that, the front axle weight, and compare to our target range. And then if there is a mismatch, the unit is going to auto self-correct on its own to make sure that auto self-calibrate to make sure that the weights being measured are matching to what the range that we preset. And then also in the event of long-term measurements, like if you're going to run your measurement for 1 year, that's 12 months or more than that, we also perform routine calibration check, which will be done like every 3 months. And then also the last part is whenever we are doing our analysis, when we retrieve our data, the first part is to do a post-check and post-calibration to ensure that the data is of good quality and it's confirming to what is expected. When we do the calibration, the various parameters we check is the vehicle class, the speed, the axle spacing, the individual axle weight, and the gross vehicle weight. As you can see here, in this picture here, we are measuring the spacing between the axles, and therefore, we expect that when the vehicle runs over the sensors, that spacing should match with what we measured, and then we know that it's measuring correct. And also here, as you can see, we are measuring the weight of this vehicle, and then for calibration purposes, we will compare and see what the measurements are going to read when the vehicle passes over the sensors. Here, this is an example of a class 9 truck, which is commonly found on the Texas road. That would be the steering axle. And for the most part, this steering axle, its weight will be fairly constant, whether the rear axles here are loaded or not. And also, this is another vehicle, which is a class 6. For the most part, the TexDot has a lot of these class 6. So we also use it as part of the calibration process. Now, this video here shows an example of a calibration check that we did just after installation. As you can see at the bottom here, you see that the static weight measured about 6,575, and the portable WIM measured 6,550 at that speed, meaning that the calibration that we performed and the installation process was fairly satisfactory. Yeah, so you can see that we have this vehicle there. We already know its weight. Yeah, we have this vehicle here. We already know its weight, and it passes over the portable WIM here. And then we compare the weight to see if they are matching or not. If they are not, then we go and change the calibration factor into the portable WIM until they match. Here in this slide, it shows the sensor pre-check and the pre-calibration process that we do before heading out into the field. These are the sensors here, as you can see there, and then we have a track there. Okay. You can see that this track here, it has got some concrete weights on it, so we can change that to also see the sensitivity of the unit. As you can see here, whenever we are doing the calibration, we always go for minimum 3 speeds, minimum 3 temperatures. One of the key issues to be worried about is that the sensors and the are temperature sensitive, and our pavement also, if it's an asphalt surface, it's a viscoelastic material, therefore it's sensitive to temperature, and so are our readings. So meaning that when you are doing your calibration, you make sure that you do those calibration at different pavement temperature, so that when you install your pavement, let's say it gets cold or it gets hot, that does not affect your readings as much, because during calibration you consider that as well. Also, in terms of the weight, we usually do minimum 3 weights. You keep on changing the weight to see any variation, and then you get a factor that is going to give all a representative reading. And we also perform minimum 3 runs per factor. So here now is an example of this very track. The front steering axle here, this one here, that's what we measured using static scales here. And then now we go for the first run, the first run at 50 miles per hour. This is the speed that was being registered on the speedometer in the truck. We made 3 runs. This is an example of the calibration factor. And here now are the portable WIM measurements. As you can see, that's a speed recorded. And here are the axle weights that we're getting. Then also we changed the speed to 60. That's a calibration factor. And these are the reading we're getting. And also we did the same here at 70 miles per hour. We keep on doing that, and then finally you get an average calibration factor, which is going to give you readings which are close to that number. And when we are doing our calibration, a pre-check, our target for the most part is a difference of about 5%. So you see that we only stop when the difference here and the measured is about 5%. So this is just a pre-check that we do before going out to ensure that your system is well calibrated and you'll be able to get a good and accurate traffic data. This year, even the number of vehicles, if we have, at times we would change different vehicles. Here it's another vehicle, a truck. It will run there, and also we'll compare the measurements. This here, it shows an example of the calibration that we did on a highway side. This was in 2014. As you can see, what we do, we measure the vehicle, that's class 6, the weight of each individual tire, the spacing, and the gross vehicle weight. We measure all that. And then after that, we make the truck run over the sensors and we do our measurements. As you can see, this here was the speed recorded from the portable WIM, and these are the weights. Axle 1, which is this one here. You can see it, that's a total. That's what we got for run 1. Then axle 2, which is here. These are the numbers we're getting. Axle 3, which is here. These are the numbers we're getting. And here we have got now the gross vehicle weight. And then we average that, and then we calculate the difference with the static scale results. And as you can see, the difference is actually less than 5%, way below our target of 15%. There is the pavement surface temperature at which this particular calibration was done at. As I said earlier on, you have to do this at multiple temperatures, a minimum of 3 temperatures, to account for the temperature effects on the readings. Here again is another example that we did as part of the calibration process. In this case, we had used 3 different tracks, class 9, class 6, class 9, class 10, you can see there. And these are the number of runs we did. And overall, after installation, the difference was a coefficient of variation of about 6%, well less than a target of 15%. And then again, we went and did a calibration check after 69 days. And again, as you can see, the variation was also still around 6%, which is less than the target of 15%. So as you can see, when you do proper calibration, proper installation, you can get results that are very close to your static weight scale measurements of the track. And this is why I emphasize that calibration is one of the key elements to obtaining quality results from the portable WIM. Now, in terms of traffic measurements, the actual data that you measure, our system can measure up to about 12 months when you install there. But the minimum that we typically do is 721 days, because during that period, you have enough traffic data for pavement design. We can also do multiple lanes at a time. The maximum number of lanes we can do from one unit is 16. So at one point, at a go, you can do 16 lanes. Also, the traffic data, we can either review and retrieve it manually, by going to the site, or remote if you have installed a modem communication system. The data output is in a simple format, which is in MS Excel. So people can actually see it and analyze it simple, because everybody else is familiar with MS Excel. This slide here now shows an example of how you see the traffic in real time from your computer. This here is the time in that column. In this column is the lane. In this case, we are looking at lane number 2. And this is the class of the vehicle. Class 9 is a truck by our Texas standard. And then class 3 here will be a pickup truck or a bus like this one. Then here on top, it's showing the speed of the vehicle, and here at the bottom, it's showing the gross vehicle weight of that vehicle. Then here it shows the number of axles, and this is the spacing between the axles in that row. And here at the bottom is the weight of the individual axle. So if I take this example, this one here is representing the weight of this axle here. This one here is representing the weight of this axle. This one here is representing the weight of that axle. And this one here, the weight of this axle, and this one, the weight of that axle. So with a portable WIM, you are able actually to see the weight of each axle as well as the gross vehicle weight. And so it can actually tell you to see which axle is mostly loaded. And in this case, if you look at this one here, you can see that this axle here is mostly heavily loaded compared to the other axles, meaning that the cargo in the truck is not uniformly loaded. Now, this video that I have here, it shows some examples of the traffic measurements that we did on different highways. We have our portable WIM installed there, and here on the side, we have the data logger. And this particular system has been in service at the time of taking this video for about 12 months. So if I click there, you see that the small car passing, and then you see there, it will show the reading there. You see, so as the vehicle passes, you are able to see the reading there. This here is the speed, and that is the weight. Pay attention to that number, which is 3,087, and also the number of axles on top there, as well as the class. Now we have a truck coming. You see now, you compare the weight of that truck, that's about 69,000, and that was the speed. And also you see class 9, and here you can see on top a bunch of axles. So from the unit, either in the office or right there on site, you are able to see on the screen the weight of the vehicle, the speed, the number of axles, and also the type of the vehicle, in this case, the class. So you see all these are different measurements here. Let me see. Okay, so here we have our sensor here and the other sensor on that direction. And also, as you can see from this picture, our sensor, the color of the tape is close to the pavement surface. The reason for doing that is so that the truckers or drivers are not going to be disturbed by the color of the sensors, or in the case of truck drivers, try to avoid passing through the sensors to avoid being measured. So that's why you see when you look here, it's not easy to define that, okay, we have our portable WIM unit there. But here you can see that's what we have in that direction. Yeah. Okay, so now you've been able to see a video example of how we conduct the measurement of the portable WIM. It's fairly flexible, portable. You can install it at any location that you want. Here again now is some pictures that show the portable WIM and the tracks passing over. This is one of the areas that we have a lot of tracks. It's an energy development area, and these measurements were done before the COVID came out. As you can see, there we've got the portable WIM, we've got the portable WIM there, the portable WIM there, the portable WIM, portable WIM, portable WIM. Here it shows that with a portable WIM, you've got the potential to install at any location that you want and be able to collect site-specific traffic data that you can use for pavement design. Now, in terms of the data output, this is what you are able to get from the portable WIM. You have got the volume counts, the vehicle speed, vehicle classification, which is the type, and then you can also get the hourly and daily distribution. You can also get the vehicle and track weights, which is very, very critical for pavement design. And also you can get what is called the individual axle weight, because the portable WIM measures the individual axle weight separately. And above all, it will also give you the track overweight and overloading statistics to know how much is being, how much the pavement is being overloaded. And also it generates the equivalent single axle loads that are directly used for pavement design. This picture here, it merely shows the vehicle class distribution as per the Federal Highway Administration. That's a class 1, class 2, and class 9. We have the class 9 here, which are the majority tracks on the Texas roads. The program for developing, for analyzing this data was, as mentioned earlier, was custom developed, and we are able to generate any desired output format. Here it shows an example of the weight distribution, and this one here shows an example of the hourly track distribution. These are the overweight tracks, and you can see you have got a peak here. This one shows the daily track distribution. You can see here the red one, which it shows the overweight tracks. You can see that Tuesday and Friday, they have got more of the overweight tracks. And then here, it merely shows class distribution of the vehicle. For the most part, as I mentioned, in terms of tracks, as you can see here, the majority are class 9. And also for the smaller vehicles, the majority will be class C2 and class 3, which are shown here. So the portable WIM is able to give you all that information. Here again is another more clear example. Here, this shows the vehicle hourly distribution for one highway in 2 directions, the westbound and the eastbound. As you can see, for the westbound, we have got a peak in the morning, and for the eastbound, we have a peak in the afternoon. This highway could be probably that it's leading to a working area like offices, and therefore in the morning, people are going to work in the west direction, and in the evening, people are coming from work in the eastbound direction. So you can be able to tell, to see which time of the day to avoid traffic congestion. You can see around that time in the eastbound, and around that time in the westbound. This again shows just the track distribution. You can see that as expected on this road, Saturday and Sunday, it are the lowest tracks, both all track consideration as well as the overweight tracks. This here shows the gross vehicle weight, how it's distributed. For Texas, anything above 80 kg is considered to be overweight. And this one here is the weight distribution for the tandem axles. And in Texas, anything above 34 is considered to be overweight. However, our experience has also shown that the tandem axles are the mostly overloaded axles, and hence the example that I've shown here. Now, let's try to talk about the data consistency and accuracy of the unit. So this here is an example of class 9 steering axle weight. As you can see, there is fairly consistency in that the traffic data is revolving around 10 kips. There is no significant variation. In fact, the coefficient of variation that we got was 9.5, which is less than the target of 15%. So it's just one highway, as you can see. This again, as earlier mentioned, is attributed to proper installation and calibration. This here again is another example, another highway. It shows the variation, the random variation of the front axle weight of a class 9 truck. You can see that this one is around 10.5 kips. Again, a COV which is less than 15%, indicating that the proper installation, proper calibration, you'll be able to achieve good results with the portable WIM. Now, for this particular comparison, this was made with a permanent WIM system against the manual counts and with a portable WIM. Here, what we have is the permanent WIM, and this is the portable WIM just next. When we did the comparison, you can see here the classification. They are fairly comparable. That the green was manual counts, that was permanent WIM, that was portable WIM. You see it's very consistent. In terms of accuracy, comparing the portable and the permanent WIM, this is what we achieved for this study, that the accuracy we achieved was actually over 95%. Again, attributed to proper installation and calibration. This slide now compares the weight that was measured, comparing the permanent WIM versus the portable WIM. As you can see, they are fairly comparable, and the accuracy we achieved here was actually 92.5%, as you can see from these plots here. You have the blue in the portable WIM, the orangish one, this one, that's the permanent WIM. And as you can see, the weights are fairly comparable. Here again is another comparison with the permanent WIM. In this line, we have the permanent WIM, and then here we have got the portable WIM, and you can see the comparison here. You can see that overall, the accuracy achieved was more than 90%. So meaning that if you do a proper job of installation and calibration with our system, which is comprised of custom board and commercial components, is able to achieve. So we're able to achieve the accuracy that we needed. Now, in terms of the number of highway sites we have done to date, this map here shows the highway site that we have done in Texas so far since 2014. As you can see, we have done a whole bunch of highways which are more than 50. So we are pretty much active with the portable WIM in Texas. Also in Louisiana, we have done some installation there and some measurements are actually going on. And these are the sites that we have done in Louisiana so far. As I said, the major benefit of the portable WIM is that it's cheap, portable, and you are able to install it at any location to generate site-specific traffic data, provided you do proper installation and proper calibration. Here again, this is an example of some installations that we did in Louisiana. You see here, we have got that's our portable WIM, that's our portable WIM, that's our portable WIM here. So you can see we are able to install all the lanes to measure traffic data at those locations which the engineer wants, or what location where the client wants. Okay. See. Okay, so ideally, that's how our portable WIM will look like when it's installed on the pavement surface. Now, this slide, although it's very busy, it shows an example of the traffic data that was measured over a 1-year period. As you can see, we started doing our measurement in September, and the data here presents up until December 21. So you can see for this particular highway, this is how the traffic loading was varying as a function of time. Here at the bottom, that shows the variation of the class 9 front axle weight, the steering axle. You can see that the weight was fairly consistent, with only a COV of about 7%. So meaning that the portable WIM was fairly accurate in the weight measurement for all that period. And the trick to this is, as mentioned earlier on, whenever we are doing long-term measurements, like more than 12 months, we have to go and do manual calibration checks every 3 months. So that's why we're able to get all these good results. And also, as you can see, the average gross vehicle weight for a class 9 truck did not vary as much, as you can see from that plot. This here at the bottom, it shows the daily truck distribution for that particular highway. So on average, you can see that Tuesday has got more trucks, and also it has most overweight. And then Saturday and Sunday, you have the least number of trucks. In terms of all the vehicles, the same trend was observed, that Tuesday had the highest number of vehicles, and Saturday and Sunday, it was fairly not as much. Again, this is considering that this road was going to an industrial area, but a different set of results will be obtained if the road was heading, say, to a shopping mall. We will see that Saturday and Sunday, they may end up having more traffic. This year, I showed an example of the traffic that we measured per highway, per lane. So as you can see, this in this direction, these are the traffic number that we measured, and this direction, these are the traffic numbers that we measured at that location. So with the portable WIM, it's able to tell you at that location what the traffic parameters are that you can use for pavement design. Here, it's a road that has 2 lanes in each direction. The expectation generally are that most of the trucks are going to use the outside lane, which you can see from here. You have almost 700 trucks versus 200 in the inside lane. By US standards, this is the inside lane, that's the outside lane. And also, if you look at the daily equivalent single axle load, you see that this one is about 1,200 versus 152, meaning that you have the outside lane taking more loading than the inside lane, which is typical for roads having 2 lanes in one direction. Also, the same here, if you compare lane 1 is the outside lane, lane 2 is the inside lane, again, you see that the outside lane has more truck traffic, which is this one here, the ADT, versus the inside lane, which is only 184. So again, this shows that the portable WIM is able to measure and give trends which are within normal expectation. You see here the daily ISOs here is about 900 versus almost 200 in the inside lane. And also I must mention that for pavement design, for the most part, we always use the outside lane, which mostly carries the highest number of heavy trucks. Now, to conclude the presentation and summarize, this presentation has demonstrated that the portable WIM is a cost-effective technology for site-specific traffic measurements and data collection, particularly for pavement design, rehabilitation, and maintenance. With the portable WIM, you are able to install at any specific location that you want to measure your traffic. Therefore, it's very, very ideal for project level type of data. You are not going to do estimation like you use another highway or empirical methods to try and determine your traffic data. In terms of reliability and accuracy, our system is able to achieve over 90% accuracy, which was validated by comparisons with a permanent WIM. And also, in fact, we did comparisons with other systems such as Webtronics, Bridge WIM, etc. And this high accuracy is, for the most part, attributed to proper installation and calibration are the key to obtaining quality results. In terms of data collection, with the system, we typically do 721 days up to over 12 months, depending on the specific need for that project. However, 721 days of traffic data has proved to be adequate for the purpose of pavement design. If we are doing over 12, up to 12 months, usually we'll do periodic maintenance, such as calibration checks every 3 months. Also, the program that I use for analyzing data, all these are custom developed and they can be reconfigured and retailored to whatever is needed for a specific project. In their current format, the programs, they generate ready-to-use traffic inputs for various pavement design applications. So the traffic data that is generated, one will be able to directly use it for pavement design. And lastly, as mentioned, this is a low-cost technology, which is very good for supplementing static wave bridges and permanent WIM stations, especially considering that the wave bridges and permanent WIM stations are very expensive. So this one would be very ideal to supplement that, and also the ability to install it at any location that uh, one desires to collect traffic data. The picture here on the right side, it shows the complete package of the portable WIM. We have the sensor there. We have the solar panel for powering the unit, and that's a control box. And then we have the static scales for calibration purposes. And then last, we have a computer uh, for data storage and analysis. That concludes my presentation. Okay, that's the end of my presentation.
Hold on a second, Lubinda. Let me check here and see if there are questions from the audience, and we'll continue. All right. So stand
Okay,
by. Okay.
okay.
Listo. Si hay preguntas. We are waiting for any comments from the audience. Let's check and see. Igual que la vez pasada, que funcionó perfecto. Our the person who's talking now, we've been working about asphalt, and we've been talking about the material behavior, but not much about traffic. We, the designers, we are designing with factors from 1996 to update the damage data. That's what we need. What you are showing us, measuring the axles, how much does an equipment like this cost? Instead of buying a deflectometer, we buy this equipment so that each region has one. And if you could give us a discount, so please.
Oh, oh, okay. I think that one.
Okay, creo que esa.
That's a very good question. I think in terms of the cost, we can talk later on the side. But yes, for the most part, everybody else around the world, they are using estimates which were done long time ago, and the traffic nowadays, it keeps on changing. So that's why it's very important. Not only should we focus on the material design, but we also need to focus on getting accurate and correct traffic data as the key for our payment design. So I'll provide the cost, email the cost estimate, and if there are any need to purchase one or to help out, my contact details are provided here. Yeah. Oh, sorry. So, sorry about that. My contact details are provided there. But what you are saying is very right, that we should not only be looking at the material component, but also getting accurate and traffic data is very, very important for ensuring that our designs are perfect. One example that we had in Texas was that we had a road which was designed using old traffic data. And when the road was open to traffic, it failed within 3 years. And when we went to measure there the traffic, we found that the traffic was about 6 times more than what was estimated. Let me see if I have that example here. Yeah, yes. Let me make it big. Yeah, this road here, it was initially designed using traffic estimates from the old method. And the road, it failed, as you can see, within, let me see, how do I show? Let me see. Okay, hide. Share window. Okay, share. This road here, when they did the design, they are designed using traffic that was estimated from the old methods, no measurements. So after 3 years, as you can see from the picture, this road just failed. When we went to measure the traffic here, we found that what they used for design was about 6 million. They used 6 million for design, but what we measured over a 20-year period was actually 25 million. So we found that the traffic in terms of ISOs was 6 million ISOs versus 25 million ISOs. So that's why the portable WIM is very, very critical to ensure that you are able to measure accurate and correct site-specific traffic data to ensure that your designs are accurate as well. Okay, any more questions?
Let's wait and see if there is another question. Hold on.
¿Más preguntas?
There is another question, so let's wait.
Okay.
Okay, my question is, as we all know in the traffic studies, last developments, we do it with AI from cameras that based on the vehicle's length, you could check the type of vehicle. I like to know if the portable WIM could classify the types of vehicles, because somehow this has to do a lot with the traffic behavior in the urban roads.
Okay, that's a very good question. And the answer to the first question is yes, the portable WIM is able to classify the vehicle type. So we are able to do that. Second question, the portable WIM, it has got an option to install a video camera or the LiDAR system to take pictures and all that is needed. However, in the Texas, for the current project that we are doing, the client does not need that. So if, for instance, the client says, I want a portable WIM, but I want it to have a camera to be taking pictures and so on, we can do that. That's an optional component that we add on. But for the current measurement from the state of Texas, because of legal issues, they don't allow us to take pictures of people or the vehicle number plates. but that is an option for the client. So answered question number one, yes, the portable WIM can classify the vehicle types. Answered question number two, yes, the portable WIM has got an option to include a video camera or a LiDAR system that you want to include in that. Otherwise, the portable WIM is able to measure the axle spacing of the tires, and from there we are able to classify the vehicle types.
Okay, let's see. We are waiting if there is another question. Yeah, it seems like there is another question, so hold on a second. Good morning. You mentioned at the beginning of your presentation that for locating the WIM, you should do it in a good adherence surface like a hot, warm, so that the tapes adhere to the surface. So, what methods or how could you do this in a region where there is not this good temperature, like cold weather, to install it?
Yes, that is a very good question. So if you are installing in very cold weather where the temperatures are very warm, what we do is we heat the pavement. We have a heating unit so that at that location where we're installing, we are going to heat the pavement to warm it up so that we can be able to attach the sensors. But the reason why I said that is if you can avoid that, you are better off installing in summer. But if you want to do in winter, we have that option for a heating system that will heat the pavement at that location, warm it up, and then you do your installation. Except
Okay.
except
Eh,
except it adds more work to you. But otherwise, we have that option that we have done it in winter, heat the pavement at that location, warm it up, and then now do the installation.
Okay, Engineer Lubinda, we thank you very much for your presentation. People here are excited about this equipment. Thanks. All right. Okay, so we finish. Again, thank you very much for your
Okay,
excellent presentation.
most welcome. Thanks
Hold on
very
a
much.
second. Hold on a second. Hold on. It seems
Oh,
like there are more questions, so
okay, okay,
hold on a second. Don't leave. So
okay.
we have more questions. All right. Here they are excited about your presentation. So, man, that's good news for you. All right.
Lots of questions. Yes.
Well, I don't think that too many.
Okay, okay. Are we not running out of time? Who is the next presenter?
Hold on a second. Hold on a second. Disculpa. Aguanta. Que estoy aquí tratando de manejar canales. It is clear for us that the scale should be placed on flat surfaces. All right. Yeah, but I would also like to know what's the maximum slope that you could have, taking into account that many of the roadways in our country are located in mountains zones. So what's the maximum slope that you should have?
Usually we do up to about 2.5%. We have done about 2.5%. Here in Texas, we haven't gotten anything way higher. So the experience I have myself is maximum 2.5%.
Okay, it seems like there is another question. Someone who wants to finish. So let's wait and see the last question. That will
Yes,
be
but But
Hold on. Tell me. No, it seemed like okay. It seemed like yeah, we finished. Lubinda, Walubita, thanks very much for your conference, for your time to clarify questions. So it is a very interesting topic, and thank you. All right. So
okay.
kind regards. Take care. All right.
Well, if there are more questions, they can just email to me. I'll respond. You have my details, right? They can email me. Yeah. Okay.
All right. Take care. Bye
Okay.
bye.
Bye. Bye. Thanks.